All right, so the last reaction that we saw in our last class sessions would have given us enough information to be able to do things like think about a reaction where we've got an alkyl halide and different bases, right? So for instance, if we treat this with sodium ethoxide and some heat versus tert butoxide, right? We would have two different beta positions that we could look at, right? And depending on which one of these beta hydrogens we abstract with a base, we would form a different elimination product. So secondary alkyl halide, right? Strong base, but it's a small base. And so on something like this, we are going to be forming the more stable alkene. So since this sodium, or since the ethoxide is not a bulky base, it doesn't have difficulty getting in here, plucking off that proton to form the more substituted alkene. Whereas with tert butoxide, right, that tert butoxide has that big bulky tert butyl group on it. It has a more difficult time getting into that more substituted position, and it will instead form as the major product this one. Right? And we referred to this product as the Zaitsev product, and this product as the Hoffman product. Right? So these were E2 mechanisms, both of them. Okay, and then another example would be if we use a tertiary alkyl halide, and if a tertiary alkyl halide with a strong base would still proceed via an E2 mechanism. But if we use a weak base, so just ethanol itself without that ethoxide base, this is going to go via an E1 mechanism, where we lose the bromide first to form a carbocation, and then a neighboring beta proton is abstracted by the weak base. Like so. And again, the Zaitsev product's going to be the major product here. Okay, so that was dehydrohalogenation. And when we were looking at the E2 mechanisms, right, we said E2 specifically is going to prefer stereochemistry where we have our proton that's being abstracted and the leaving group anti-coplanar. This particular example where we have a linear type structure, we can rotate around this sigma bond. And so it's easy to rotate this so that that chloride is actually anti-coplanar to the proton. Okay, this was best illustrated by using cyclic structure. So we had cyclohexane derivatives with a leaving group, and we were able to show that anti-coplanar relationship. So the problems in the chapter at the end of that unit, let me quick remind myself what page it's on for you. Page 303, problems 710 and 711 are really good to make sure that you really understand that anti-coplanar relationship. Okay. And if you have forgotten this content, I did post the recording of one of the classes where we went through this, so you can go back and review that as needed. Okay, so what we want to do today is push ahead with a mechanism called acid catalyzed dehydration of alcohols. Okay, and it's another reaction where, I should actually say two mechanisms. Mostly we're going to be looking at E1 type chemistry, but there will be some cases when we see some E2 popping in. Okay, but overall what we're doing is an acid catalyzed dehydration. Okay, and we'll be using alcohols as a substrate. And what we're going to be, let's see, so we're going to start out with an alcohol. What we're going to be forming here are alkenes. Okay, so these are, again, elimination reactions. And we've seen before that alcohols with that hydroxyl group, right, that hydroxyl group is not a good leaving group. And so what we're going to do is protonate to make this a better leaving group. So when we do that, that's going to become an OH2 plus, right? So essentially what's going to be happening is we're going to have this come off as water, and water is a weak base, so it's going to be a better leaving group. Okay. Depending on the type of alcohol we're looking at, is going, that's going to determine the concentration of acid that we need and the temperature that we're going to need in order to accomplish an elimination. Okay, so some alcohols will eliminate easier than others. Okay. So here's just the generic overall reaction. So we've got the hydroxyl group of an alcohol, and then in a position next to it, we have a proton. We'll use a proton source that comes from acid to make that hydroxyl group a better leaving group, and we will heat it up. And remember, this delta is the symbol for heat. Okay, and we will form a molecule of water. Okay, so these are acid catalyzed. So that means the proton here, this acid, is helping the reaction go, but it's not being used up, right? So we put a proton in to help things along. We get a proton back out at the end. Okay, so when we talk about the nature of the alcohol, what we're talking about is it a primary, secondary, or tertiary alcohol, and that's really going to help dictate what the reaction conditions need to be. So let's take a look at a few examples of different reaction conditions. So for instance, a primary alcohol like ethanol takes quite extreme conditions, actually. So we use sulfuric acid in its concentrated form, and we heat this up to 180 degrees Celsius. That's well above the boiling point of water. Nice and hot. And that will give us ethene as a product. And we will work through the mechanisms here in a minute. Okay. Now, if we switch to a secondary alcohol, so maybe something like cyclohexanol, now we can get away with a slightly weaker acid like 85% phosphoric acid, a little bit lower temperature, 165 degrees, and we will get cyclohexene as a product. Okay. Let's see, we get about 80% yield on something like this. And then for a tertiary alcohol, like tert butyl alcohol, this one, we can get away with 20% sulfuric acid and quite a bit lower temperature. So something like 85 degrees Celsius will work. And that will give us this elimination product in about an 84% yield. Okay, so from looking at these conditions, it should stand out that the relative ease of dehydration depends on the substitution pattern on those alcohols. So we would say tertiary alcohols are easier to dehydrate than the secondary alcohol, which is easier to dehydrate than a primary alcohol. Okay. Now, it is important to remember that when we say something like a dilute acid, right? So something like this, 20% sulfuric acid, that implies that that is in water, right? And dilute acid in water forms hydronium. So really the reactive species we would be talking about in this case for our mechanism is hydronium. It's not the sulfuric acid. Okay, because as soon as you put sulfuric acid in water, it's a strong acid. It completely gives up its proton to the water to form hydronium. Okay, and then before we actually write a mechanism, I just want to point out one other thing that we're going to be watching out for. Okay, so we're going to see that in some cases, the carbon framework of a molecule can rearrange when we're doing these dehydration reactions. So for instance, if we take 3,3-dimethyl butanol, 2-butanol, and we do a dehydration, it turns out that our products that we get are these. Write that a little bit cleaner. So we get about 80% yield of this alkene and 20% yield of this alkene. Okay. And if you look at the carbon framework, right, this 3,3-dimethyl butane basis, look at the products here. We still have a bute, right, for the 4 carbons, but look at this. Now we've got a 2 and a 3-methyl, right? So there's the butane framework and a 2 and a 3-methyl, right? So something's happened here, right? So we'll see that we go through a carbocation intermediate in this reaction mechanism. And we call it a carbocation rearrangement. What's really happening is that the methyl group in this particular case, so one of these methyl groups here, the 2 electrons that are in this carbon-carbon bond shift over to this neighboring carbon where that positive charge is. So those blue electrons are moving along with that methyl group right there, and that leaves a positive charge here at this carbon. So we call it a carbocation rearrangement, but the fact that the positive charge has moved is just the result of this methyl group and the electrons from its carbon-carbon bond having moved. Okay, so once this happens, then we can either remove a proton from this position, or there's also one right here. If we remove this proton, that gives that product. And if we remove this proton here, that gives that product. Okay, so we're going to need to account for rearrangements sometimes. Before we tackle a mechanism where there's a rearrangement though, let's first just do a simple dehydration, okay? So let me first just finish out a comment on this if you're trying to write notes. Okay, so in this overall rearrangement of the carbon framework, it is the carbocation that is undergoing rearrangement. And I'll pause if anyone has a question at this point. Happy to take that before we start writing out a mechanism. Okay. All right, so when we look at the mechanism of dehydration, what we're going to see is that when we have secondary and tertiary alcohols, our mechanism will proceed via E1. Okay, and our substrate will be a protonated alcohol. Okay, so previously we've really been focused on alkyl halides, right, as substrates, where our leaving group is the halide. In this case, where we're starting with alcohols, before we are able to do these eliminations, we first have to convert that alcohol into the protonated alcohol. And that is going to allow the hydroxyl group to become a better leaving group, right? So water is going to be the leaving group. Okay, so for dehydration of these, that's the first thing that's that we're going to have to do before we call this a substrate. Okay, so let's take tert-butyl alcohol and use that as an example. Okay, so for tert-butyl alcohol, it's also called tert-butanol, and the formal IUPAC name, we would actually call this a 2-methyl-2-propanol, right? But tert-butyl is a pretty common name, so we call this just tert-butanol. So tertiary alcohol, typical conditions would be dilute, acid, and we will form two-methyl propene as a product. Okay, so how does this happen? Remember that we said dilute acid is hydronium, right? So the first thing that happens is, let's see, let me write out phosphoric acid once. Right, so you put phosphoric acid in water, that water will accept a proton right away to form hydronium. And so that's what we want to use when we write our mechanism. Okay, so proton transfers are very fast. Okay, so this first process where we protonate this alcohol is going to be a fast process. You do need to be precise in your arrows. The last quiz, there were a few sloppy arrow pushes in your mechanisms, right? You want to always be starting right where a pair of electrons is, either as a lone pair or in a bond, right? So your arrow starts at the electrons or at the bond. And let me fill in the lone pairs here as well on the original alcohol. So this now has a lone pair and a plus charge, right? And we've produced a molecule of water. Write that off to the side there. Okay, so again, proton transfers are fast. They're also reversible. So we're using reversible arrows to show that this process goes back and forth. Okay. Now, once we form the protonated alcohol, this is what we refer to as our substrate, right? Because now we've got something with a leaving group. This next step is slow. Okay. And what we're doing is dissociating water. So pair of electrons in the carbon-oxygen bond leave with the oxygen. And that leaves behind a carbon that's electron deficient as a carbocation. Okay. So we're forming a relatively unstable intermediate in our carbocation. So on a potential energy diagram, what's happening here? Well, initially that alcohol gets protonated, and then that substrate, when it dissociates to give water, is forming that high energy but relatively stable, meaning it's a energy minimum on one of these curves, intermediate. So here's the protonated alcohol, here's the carbocation intermediate, and then it's a fast process to lose a proton to form our alkene. Okay, so let me draw out the details of one of these methyl groups. In order to be able to write a mechanism, I need to have access to the carbon-hydrogen bond here. So I need to draw that out in enough detail I can show it. Okay, so water now is acting as a base. It's abstracting a proton from a beta position. The electrons from the carbon-hydrogen bond here move in towards that carbocation to form the alkene. Okay, and that is a fast process. And we're forming here, so I'm going to kind of show an arrow coming out of this, hydronium, right? Water plus a proton is hydronium. So having the carbocation next to a carbon-hydrogen bond, that weakens this carbon-hydrogen bond enough that a weak base like water has no trouble abstracting a proton. Okay, so this is acid catalyzed, right? We started by putting in a proton right here. We get out a proton right here. So we don't actually use up the acid, okay? But it's critical as a catalyst, right? We need it in order to facilitate water as a leaving group. Okay, And our steps here, first, we protonate the alcohol. Second, water departs, right? Right here, the water departs. And that process, right, where both electrons in that carbon-oxygen bond move over to the oxygen, that process was called heterolytic bond cleavage, where two electrons move in the same direction. And then the third step is where the beta hydrogen is removed by water. And we want to keep practicing using the chemical terminology when we talk through mechanisms like this. So when you're, hopefully studying together and things, you're talking through these things. Okay. And then in terms of that carbocation intermediate that we're forming, right? We need to remember the details of carbocation stability. So remember we talked about hyperconjugation, right? Where if we draw out a three-dimensional structure, so let me show that carbocation intermediate from the side so that we can show that empty p orbital in the plane of the board here a little bit easier, right? And then if I look at that methyl group next to it and that beta hydrogen. So here's the methyl group. Okay, there is rotation around this sigma bond here, but it can align in a way that a carbon hydrogen, or we'll also see a little bit later that this could be even a carbon-carbon bond here, shifts electron density through space towards that empty p orbital on that carbocation. And so we said the more beta positions, right, or the more R groups, the more of that hyperconjugation goes on. And so the more stable the carbocation. Okay, so let's clear this. And just make sure we have this in the notes again. Right, that tertiary carbocations are better than secondary carbocations, which are better than primary, which are better than methyl. Okay, so when we're doing these dehydrations, right, we're going through this protonated alcohol substrate, and the charge here is localized on that oxygen. When we start to break that carbon-oxygen bond and go through a transition state, so remember, transition states are where we're partially breaking or partially forming bonds. So at the transition state, we start to lose the positive charge on the oxygen and start to form the positive charge on the carbon. And so anything that helps to stabilize the positive charge as it forms on that carbon is going to help those reactions go where we have to form carbocations. Okay, so just a little reminder, transition states are on a potential energy diagram. Those are the high point on a curve, right? Whereas an intermediate would be a relative minimum. So in a reaction involving a carbocation, it is high energy, but it's a relative, compared to these transition states, it's relatively stable. Okay, transition states are these high energy points, and normally we don't write a transition state in our mechanism unless it's an important thing for understanding what's happening. So the E2 mechanism, where we have anti-coplanar arrangements, sometimes we'll try to draw that transition state. And the SN2, like you saw on the test yesterday, we like you to be able to draw those transition states because they're important for understanding the stereochemistry. Okay, so again, this carbocation stability, these R groups are electron releasing or electron donating. And that occurs through the process hyperconjugation. Okay, so I'm going to continue my notes down here at the bottom. So the more R groups, the more stable the carbocation. And the more stable the transition state, leading to that carbocation. Okay, so essentially all that means is if you are forming a primary carbocation, right, that's going to be a higher energy species than a secondary carbocation, which is a higher energy species than a tertiary carbocation. And so those R groups are stabilizing the carbocation, but they're also stabilizing the transition states here. And so it makes them easier to form. Okay. Now, primary carbocations are so high energy that they're actually very difficult to form. And in a dehydration, we just don't see them forming discretely. So what can happen is we can actually get a variation of the mechanism where we avoid having to form a primary carbocation. So let me show you that. We're not going to use it too much because there are better ways to do the same chemistry, but I want to make sure you can see that we could avoid forming a primary carbocation if we have to. So what we're going to do is do our dehydration via an E2 step. And we saw the example of a primary alcohol when we looked at ethanol. And what I'm going to do is just focus on more generically on a primary position. So here's a primary alcohol, and let me include one of the beta hydrogens. Okay. And we saw the reaction conditions for a primary alcohol involved concentrated sulfuric acid and fairly extreme heat. Okay, so here with the concentrated acid, we're not transferring proton to water to make hydronium. So here our sulfuric acid is the proton donor. So I'm just rewriting sulfuric acid so that I can highlight one of the OH bonds. So my alcohol then is going to be protonated directly by the sulfuric acid. That is a fast process. And we are doing that to form oxonium, right? Oxygens like this. This is an alkyl oxonium ion. This is our substrate. And because it's so difficult to form a primary carbocation because they're so unstable, what we can do instead of just breaking this carbon-oxygen bond here is our hydrogen sulfate that results from giving up a proton here. Acts as the base and can take the neighboring proton, right? This is the beta proton. Carbon hydrogen electrons move in to form a double bond, and our water leaves as our leaving group. So this is a slower process, but it allows us to avoid having to form a primary carbocation. So coming out of this reaction, then we get back sulfuric acid. So we use the sulfuric acid to protonate the alcohol to make substrate, and then we reform the the sulfuric acid here. So again, this is acid catalyzed. Here's the primary, right, or the terminal alkene that we're forming. And we have eliminated a molecule of water. Okay, so we're only doing this E2 in a dehydration to avoid forming the primary carbocation. Are there any questions on how we either did the dehydration via E1 on our tertiary alcohol, or how we do the dehydration via E2 here on a primary alcohol before we tackle rearrangements. No questions? All right. So what happens in terms of molecular rearrangements? Okay, so it's the carbocation stability that drives this. And generally what we're looking at is a secondary alcohol. Okay, so let's use an example. Let's go back to that example where I showed you the skeletal rearrangement already, the 3,3-dimethyl-2-butanol. Okay, and I'm going to, let me clear my text here to give us maximum room to draw our mechanism. So I recommend that you use condensed structural drawings, at least initially, before switching over to bond line drawings, because you really want to be able to keep track of all the atoms and charges and all that stuff. Okay, so we said that the products we formed here were these two different alkenes. And we said that this was the major product and this was the minor product. Okay, hopefully that makes sense. The major product here is the more substituted. Right? An alkene that has 4 R groups on it is more stable than an alkene that has 2 R groups on it. So we can also say this is more stable and this is less stable. All right, so what happens? The first step in the dehydrations is protonation of the alcohol, right, to make our substrate. And this is dilute, looks pretty strong, but it's not 100% phosphoric acid. So we're going to use hydronium as our acid source. The alcohol takes a proton from the hydronium. This is a fast step. And so we're forming the protonated alcohol right here, which is going to be our substrate, right? And now that we have a decent enough leaving group, the water can dissociate as a leaving group. This is a slow step. And this carbon right here has 3 things bonded to it and is a carbocation. Okay, so now here's where the rearrangement comes in. So this secondary carbocation is less stable than tertiary carbocations. And so what can happen is a bond next to it so this carbon-carbon bond right here can shift over. So the 2 electrons in the bond, along with the CH3, shift over to that carbocation. So here are those 2 electrons in the bond. That's where they end up. And so what that does is leave behind a carbocation right here, which is a tertiary carbocation. And so that's the driving force for this rearrangement. We're going from a less stable to a more stable carbocation. Okay, so now let me draw out a few details. So what we want to be able to show is exactly how we are forming those 2 products. So let me highlight one of the hydrogens here on this methyl group, and then on this carbon, let me highlight its bond to that hydrogen. Okay, so in the last step here, water is going to abstract a beta hydrogen relative to the carbocation. So this position here, when we abstract that hydrogen, the electrons from the carbon-hydrogen bond move in here to make the pi bond right there. Okay, now there are also beta hydrogens on these methyl groups. So here I've highlighted one. And so we also get some of our product forming by water abstracting one of those beta hydrogens to form that alkene right there. And hopefully it makes sense that the preference is to form the more substituted, more stable alkene, right? That process is going through a transition state where you're forming a more stable alkene, so the transition state itself is stabilized. Okay, now let me focus a little bit more on this carbocation rearrangement. So how is it that, I'm just giving myself a little more space to write here, how is it that this rearrangement happens? Right? So if you think about that hyperconjugation, right, where next to a carbocation, you can have a sigma bond, either to a hydrogen or, in this case, right, we've got methyl groups out here. And so you get hyperconjugation here between a carbon-carbon bond and that carbocation. And so what's happening here is, if we draw the transition state, we're starting to form the bond between this methyl group and this carbon. And we start to break the bond between this carbon and the methyl group. Right, so we're starting to break that bond. And so we're starting to lose that positive charge at the original carbocation, and we're starting to form a positive charge at the new tertiary carbocation. So this is what that transition state would look like. Okay, and so we talk about this as a methanide shift. Okay, and methanide is this thing. So it's the methyl along with the pair of electrons. And because of that pair of electrons, if we take this totally off the molecule, gives it a negative charge. That's why we call it methanide. And it's very similar to this, right, which is hydride. And we will also see hydride shifts, where instead of shifting a methyl group, we'll shift a hydrogen. So methanide shift, and this is an example then of something that we call a 1,2 shift. That just means that the shift is happening from one carbon to the one right next to it, right? So 1,2. Okay, so that's how we get these rearranged products in a dehydration. Let me say a few more things about this then. So when we look at our product distribution here, okay, we actually can get an equilibrium, right? We're achieving an equilibrium between two alkenes here. And that is under something called thermodynamic control. And we end up following Zaitsev's rule to get our more stable alkene here. Okay, so when we talk about an equilibrium being achieved, so I'm drawing these equilibrium arrows here, what can happen is if you happen to abstract the proton here and go this path and make this less substituted alkene, you can actually put a proton back on that alkene. So hydronium can actually donate a proton back on that alkene, and then you get this carbocation again, and then water can take the more substituted hydrogen here to form the more stable product. So this is an equilibrium that goes via the carbocation intermediate. Okay, so we say this is under thermodynamic control because it's the stability of the product that is determining this ratio, right? So whatever this product distribution is. And so we're going to favor that more stable Zaitsev product. So we also, again, we said that we can do methanide shifts, right, where we have alkyl groups shifting. We can also do something called a hydride shift, though. So I want to write out an example of that in our last 10 minutes. Whoops, sorry, get back my whiteboard full size here. Okay, so both alkanide, and that would be, for example, the methanide, but an alkanide is any alkyl group with that extra electron. Okay, so for an alkanide shift, that would be what we just showed you, where, for instance, we have a methyl group next to the carbocation, and that's what's shifting. So there's the bond, right? That's shifting over here. And so this one is specifically a methanide. But if we had, say, instead of methyl groups here, we had ethyl groups, an ethyl group could shift, and we would call that an ethanide. And here we went from a secondary carbocation to a tertiary carbocation. Okay, but let me give you another example. In this case, we have a carbocation, and we've got methyl groups and a hydrogen next to it. And in this case, we're going to do a hydride shift. And we're doing the hydride shift by taking, same kind of thing, taking the electrons in this carbon-hydrogen bond, shifting them over right there. And that again allows us to go from a secondary carbocation to a tertiary carbocation. And it's the difference in stability, right? It's gaining stability by going from a higher energy secondary carbocation to a lower energy tertiary carbocation that is the driving force for this these kinds of shifts. Okay, now notice here that if instead of doing a hydride shift, we tried to do a methanide shift on this particular structure, what we would get is this thing. Okay, and this path, this doesn't help us at all because we've gone from a secondary carbocation to another secondary carbocation. That's not any more stable, so that's not, we're not gaining anything by that. So that path does not happen. Okay, now these can get a little trickier because in a cyclic, when we have some cyclic structures, we can actually do alkanide shifts that lead to ring expansion. So when we have a ring that has some angular strain in it, right, from being like a smaller ring, we might be able to do an alkanide shift and actually expand that ring